additive, no, y, e, n. So when I say E the commutative noise, I mean with respect to the addition structure that we checked. And okay, I will not say the full solution of this exercise, it's a bit long, but as a basic, and when the first thing that you can ask for what's the unital element, and here we probably cannot answer what is the unital element.
The composition, right?
We need to find element here, which we call the zero-morphism, which will back the addition. So what's the zero-morphism? Just a morphism, the unique morphism that passes through zero. So we have just one morphism here. This is called the zero-morphism. So if you have category with zero, and two objects have the zero-morphism. And if it's semi-additive, this zero-morphism is neutral with respect to attention. And of course, it's just an easy part. Now we have to prove that it is commutative and associative. Associative probably would be very cumbersome, but very straightforward.
Why is the semi-additive category called semi-additive and not additive? Because it can add any two morphism.
And you're right, but the answer is in this definition. Semi-additive equals C. Additive if or any object more fine.
Is not
In a big. So the both could have been called additive, but this kind of look nicer condition. So this is additive category and semi-additive.
P1 plus P2 needs to be P2 plus.
What?
P1 plus P2 needs to be P2 plus P1.
No. The abelian part is automatic because it's always commutative with the group part is automatic, זה עובד ואנחנו בפנים? אנחנו בפנים ואנחנו בהקלטה כבר? מצוין. טוב, אז למי שרואה את ההקלטה, for anybody that see the recording.
לא נראה שמי שנכנס, מי שנכנס היחיד זה, ביקשתי ממנו שיבדוק ששיעור טוב.
הבנתי לו, אני רק רוצה להגיד מבחינת ההקלטה, כי אם אחד השיעור רוצה הקלטה. So in the middle of the second lecture, or in the beginning of the second lecture of like second hour. So first hour is not recorded, you probably can see it in videos from previous years, which is recorded, but not exactly the same things. Oh. So, so this is the notion of additive categories. The notion of semi-additive category is less common and probably is a later notion because so at the beginning, or I think even now there is this notion of quasi-additive category. I think I'm saying the correct name. Quasi-additive category is just category with the structure of an additive group, of a abelian group or more, and such that the composition will be homomorphic thing, or bihomomorphic, everything what it means. But you do not require product for product size of different elements. And then it's not an actual a property of category, it's additional structure. And now if you so additive category is something that both have this and you have product for product one and work together. So the notion of additive category is more like useful notion, and semi-additive is kind of technical thing. Usually. Okay, so now, yes, like, the group prisms, somewhere it's the same, somewhere else. Why should you guys? You know, so then it's no, opposite with respect to addition. So, and if you have phi from x to y, you have negative phi from x to y. X to y, but it's in the same direction, then you ultimately get here. So let's say in vector spaces, morphism from x to y is matrices, and from y to x is transpose matrices, which are isomorphic but very different. And once you go to groups, it's just completely different, abelian groups. From Z to Z modulo 2, you have two morphisms, and from Z modulo 2 to Z, you have just the zero. So another exercise, the composition. This is also true in any semi-additive category. You don't know additive, but that's the composition, and behaves well with sum. So what does it mean? So write it F1 plus F2 composition G equal to what you would expect it to be, plus composition G plus composition G. And the other way around. F1, 2, B. Straightforward exercise, not very short because not how not short here because what stuff. And but this is problem. Okay. So these are the categories. Let's do examples of additive categories. So abelian groups, vector spaces, topological vector spaces, modules of administrative algebra. Yeah, these are all the examples of we discussed before sheaves. So, but we discussed about sheaves of sets. So there is a notion of sheaf of groups, so sheaf of abelian groups, the sheaves of abelian groups also. Okay, let's go to abelian categories. No, before abelian. Let's revisit the notion of image and co-image. So in additive categories, probably also in semi-additive, you can find in a different way notion of image and co-image. I didn't check it, but or basically sure that it's the same notion as image in general.
Here, take the sample which defined there in the field of ideal category.
Yes, yes. Brilliant category is, but we didn't discuss brilliant categories yet. Additive category is semi-additive category, such that the sum here is gives a good form.
So the only difference is here we don't know if we have some inverse evidence.
Opposite, so okay. We don't know. Here we are, but just the fact that this is isomorphism gives us a structure of a sum. It's automatic monoid, but we don't know whether any morphism have a morphism, not inverse.
It's like a semigroup, and if it's a group, it's a symmetric category.
It is additive category. Semi-additive meaning semigroup, and additive meaning. So, where were we? Image and co-image. So before image and co-image, let's discuss kernel. So in additive category, in general, any category with zero, we can discuss kernel. Kernel of phi. Any guesses how to define kernel of phi? Well, phi is y. X, y, phi. How to define the kernel of phi? Take the math for height is zero. Why zero? Delta is 1 0
Maybe
I think.
going to care. There's a lot of business. It's and from care to P to Y is
So what do we expect from a kernel? We want to map to X. It's a sub-object of X, so we want it to be a homomorphism. And we want that the composition will be the zero map. We already know what is a zero map. It's the map that factors through. And this is correct, but it's not like you don't really want to define it in this way because the notion of monomorphism is it's not necessarily uniquely defined in this way. First of all, it's usually not uniquely defined because you always can take a zero object. You have a monomorphism here, but then so you want the kernel to be the largest possible thing, and then you don't really care about monomorphism because largest doesn't really mean largest. You want the kernel to be terminal, so you will consider all diagrams like this. So here and morphism here, and among all these diagrams, you want the terminal and you want the terminal object. So you consider all diagrams. This commutative diagram like this, and the terminal object. So Ker phi is such an object, such a diagram, such that for any other diagram like this, you have a unique morphism. For you, so in the terminal kind of make it largest, but of course not really largest because you can take something much larger which all maps to zero. And it will not be monomorphic, but we need that to be monomorphic. Any questions? You wanted to ask or you wanted to answer?
Okay.
Okay, so this is the notion of kernel, and one could expect that morphism is monomorphism if and only if its kernel is zero. What do you think? To what extent it is correct? Not correct. In some generality is not correct, so kernel you can define any category with zero. And if you have a category with zero and you have a morphism with zero kernel, it doesn't really mean monomorphism. And the easiest example is when is the category of pointed set. So in the category of pointed set, what is the kernel? By the way, the kernel doesn't have to exist in general. If it exists, it's unique. So unique, of course, unique up to unique isomorphism, and the isomorphism is unique when you consider getting with the map here.
It's everything that goes to that point.
Exactly. So if you have pointed sets, the kernel is everything that goes to this special point, and it might be the zero object, so just a special point, and it still doesn't mean that the map is one-to-one because other points can have many points. But if your category is additive, then and the kernel is zero, then the morphism is monomorphism. Okay, I didn't check it, but I'm sure it's true, and they more sure it's easy. For semi-additive, I'm less sure it's true, but if it's true. So exercise. And if the additive and there be equal to zero. Equal to zero means that it's a zero object together with an equal. Then be equal to so kernel is something that measures at how far the morphism is from big monomorphism. You don't have it in general category, unlike image, but you do have it. And categories to zero, but not very useful there, and you do have nice categories where it's very useful. This is the and guess is what is co-kernel? As usual in category theory, co-kernel is a kernel inside. And here I have to say something that another exercise. If C is additive, so it's a category. It was also basically also accepts kind of yeah, maybe something has to be said. Because both and components are the same, so everything can change. And so a category is additive. So co-kernel is a kernel in the object category, but let's spell it out. We have from X to Y. So the co-kernel is an object here. This usually will be, this will be an epimorphism, but we don't require it. It will work automatically. This composition has to be 0. And C is a initial object in the category of such here. So the co-kernel is the initial object of such. Well, this is fixed and this fixed piece. So on the practical level, you know what is kernel of a map between, say, a billion groups. Do you know what is co-kernel of a map between a billion groups?
Factor of equal by image.
It's a factor of the target by the image of the node. Yes, so what does it mean? We take Y and we quotient it by the equivalence relation or by the subgroup, which is an image of this thing. So for billion groups, you always have a co-kernel. For groups, do you always have co-kernel? Happens to be do.
It must be normal subgroup.
So if it's normal subgroup, then you take the quotient, but in fact, you can define co-kernel in any case. You just take the normal closure of this group, like the normal subgroup, smallest normal subgroup generate. You will include the group and then quotient rate. Because what do you want? You have two maps. You have a map from X to Y. And suppose you have some group Z such that this composition is 1. Then this map have to, so the image of X has to be inside the kernel of this map, but the kernel has to be a normal subgroup, so all the conjugates X also have to be in the image. So this map has to factor through Y modulo F of the subgroup, the normally generated group. Like, so we do have co-kernel category of groups, but it's kind of weird, and in the category of abelian groups, it's the thing that you expect to be the quotient by the image. Now we have kernel and we have co-kernel, and finally we can define image in terms of added for other categories. How do we define image for other categories? Addition. B. Now I always confuse either it's the kernel of the co-kernel or the co-kernel of the kernel. So I think it's a kernel of the co-kernel. Yeah. I need to explain what do I mean by this, because a co-kernel we consider that an object, but it's not just an abstract object, it's an object together with a morphism. So we have X, we have Y, we have here. Oh, yeah, I have P, and we have this morphism, which we also by use notation called co-kernel P. And then we have the kernel. This one. And this is, so the kernel of this morphism, let's call it new. Kernel new is defined to be the image. It looks a bit weird, but let's do the exercise in the category of median groups. What this thing is? We have a map of V from X to Y. We have this co-kernel. which is exactly the which is exactly the quotient by the image. So the kernel of this map will be okay, and this is definition of image. It is the correct definition in additive groups, in additive categories. It's not the correct definition in categories in zeros in general. You can see because yeah, because for general groups, non-abelian groups, and just said now that co-kernel is not the quotient by the image, it's the quotient by the normal subgroup by the image, and that's the usual definition of image. That's a general definition of image. We'll just give you the image in groups. But in additive categories, this image is the same like the image in groups. Again, it's something that again check, but I think it's a good exercise. I will try to do it the next time, and you also do it. To definition of image. Categories. So for additive categories, it's more common to define the image as the kernel of the co-kernel. And then there is a notion of co-image, which is the image in the opposite category, and which is exactly like is the kernel, the co-kernel of the kernel. So let's do it. Co-kernel of the kernel, we have map from X to Y. We have here the kernel, and the co-kernel of the kernel is a quotient of X by its kernel. And you probably all remember the first isomorphism theorem that says that the quotient of the source by the kernel of isomorphism is isomorphic to the image of the morphism. Not only abstractly isomorphic, it's canonically isomorphic, so the natural morphism between them is isomorphic. And this is not necessarily true in any other category, but some additive categories is true. And this leads us to the notion of abelian. So maybe before notion of abelian categories, any questions? You know? Well, kernel, image to image.
Kernel only define additive.
So definition you can make of kernel for any category with zero, but it makes more sense for additive categories, so at least for that. So abelian category is definition. Abelian category. It's category with kernel, it's additive category where you have kernels and have kernels. So the fact that we define kernel doesn't mean you have it. So we want always to have it. So you have kernel, you have a kernel, and the natural morphism between the co-image and the image is an isomorphism. So maybe I should say why you have natural morphism between the co-image and the image. X, Y, C. So the co-image is this. And the map here, such that this composition is the image. So the image is a kernel of the co-kernel, so the co-kernel is this composition is zero. So why you have a morphism between the co-image and image, and probably you have two reasons. So one reason we consider the image. If image is terminal object in this situation. So in order to construct the morphism to the image, what we actually need to construct, we need to construct a morphism to Y, and such that this composition will be zero. This will give us a uniform or a morphism here. So how do we construct a morphism from the co-kernel to C? So the for the co-image to C. So what is a co-image? Is it's initial object in all the diagrams like this. So if we want to construct a morphism from the co-image to C, we have to construct the morphism from X to C, such that this composition. Okay, now we're done. Yes, because we have this composition. So we have a morphism from X to C. This composition has to be zero because already this is zero, because this is kernel. So we get a map from the co-image to C. And this composition, sorry, from co-image. No, sorry. I went too far. We want to map from co-image to Y, not to C. We want to map from co-image to I, so we need to construct a map from co-image.
Have the zero map, zero morphism we always have.
We have map from co-image to I. So, no, we just need to show that this composition is zero. And then we will get this. What do we have from co-image to? So this composition is zero because of what we said before, because it is this composition. Does we should composition zero? Sorry. We know that this composition is zero. So why this left from X to the core image? Sorry, for core image to C is zero. For example, because it's in vacuum of it. Yeah.
What sort of map do we have for
I want to decide a map from the core image to I. So I need a map from core image to Y, such that this composition is zero. So core image to Y, and do I have such map by no, by definition I don't have such map. Yeah, so I draw it here, but it's not the one. Yes. For core image to Y, in order to construct a map from core image to Y, okay, I need to construct a map from X to Y. So from core image, so core image is the kernel, sorry, co-kernel of the kernel. So I have a map from X to Y such that this composition is zero, yes, and this gives me the map to Y. And now I need to show that this composition is, which follows from the fact that it's compositions. Okay, you can better think it's Tom, and if you will have question about it in next time, I will try to prepare it more for him next time. But the idea is that just the definition of kernel and of kernel to kernel and image for image gives us unique map like this. So unique such as the corresponding diagram is mutative when you add all the errors that basically when you add these errors. Okay.
So in the ability category, it's an
Yes, so abelian category is a category where the natural morphism between the co-kernel with the co-image, and so it's a abelian definition. Abelian category is additive category such that one exists kernel P and okay. Two for image. So right like this, it means that not just that they are abstractly isomorphic, but that the natural morphism between this and this is nice. Which is basically the first isomorphism theory for theorem for abelian groups. And so these two axioms have some names. This is called AB1, this is called AB2. AB stands for abelian, just got in this paper about what will define the abelian categories. He puts these two axioms, and then there are other axioms which sometimes people ask them, but it's not part of the definition of abelian categories. So AB3 and AB4. I don't really remember, but I will say something about it in the next hour. So this is the definition of abelian categories. Category. And okay, now exercise. And if C is abelian category, then a monomorphism, which is epimorphism, is isomorphism. X, Y, X. If you have monomorphism, which is epimorphism, or in other words, if the kernel is 0 and the co-kernel is 0, kernel is 0 and the image of everything is the same, and then the morphism is invertible. And this is so this is one direction. So if it's abelian category is satisfied, and of course you also need the AB1, but AB2 is not equivalent to this condition. So there is exercise with star, you don't really have to do it. It's some artificial example of category where this is satisfied, morphism, which are monomorphism and epimorphism are invertible, but the category is not abelian because you don't have this actual AB2. So this is the definition of abelian categories. Let's do examples. So vector spaces, abelian groups, model over a ring, sheaf of abelian groups, they are all abelian. But interesting example of additive category, which is not abelian category, is topological vector spaces. And topological vector spaces is not abelian from two reasons. So it's okay. So this is not definition of abelian category, but it's very good way to check it whether a category is abelian. Because if it's not satisfied, it's not abelian. And if it is, it's usually abelian, then you have to prove it. But maybe I come from here. So do you know morphisms from vectors, topological vector spaces to topological vector spaces, which are one-to-one, onto, but not isomorphic? So are you familiar with the Banach open map theorem? So Banach open map theorem says that if you have a map between two Banach spaces, which is onto, then it's an open map. Continuous map of Banach spaces, then it's open. Which is kind of surprising and counterintuitive because continuous map of Banach spaces says that it's bounded. So if you have a bounded ball, it goes to a bounded ball. And open maps says that something opposite, that a bounded ball includes a smaller, the image of a ball includes a smaller ball. So somehow, if it's continuous, if you have a bound for above, so automatically you get a bound for below. But you need to map to be on, so the image of the entire space has to be like that. And this is very nice theorem. And at the first glance, it basically says that okay, maybe the category is abelian, because this axiom seems to be satisfied if you have one-to-one map, which is also onto, because of the onto-ness, it has to be open. And then Banach open map theorem says that So because all areas are open, so for bijection which is both continuous and open, it means that it's invertible. Yeah, because what is the problem? Yeah, you have a map which is 1-to-1 onto, so it has to be a bijection. Seems so it is invertible, but maybe not in a continuous way. But the Banach theorem seems to say that at least for Banach spaces, and 1-to-1 and onto means iso. This is very nice, but onto in category theorem or epimorphism in category theorem doesn't mean what it means usually. Category theory doesn't mean what it means usually. You still can have epimorphisms, so maps with zero kernel, but with dense image. So you have maps which are 1-to-1 and the image is flat. Says say consider the space of all C1 functions which are continuous and the first derivative is continuous. It's a very nice norm, which is basically let's work on the interval. So the super norm of the function itself plus the super norm of its derivative. So you have a continuous map from C1 function to continuous function. It's 1-to-1. It is epimorphism, although it's not onto, but the image is dense and it's smooth function. So a continuous function you can approximate with smooth function. But the map is not isomorphism, of course. It's just not onto exactly points. So topological vector spaces is not navigable. And this is very general phenomenon. Category theory in mathematics, each time you have some topology, some things that where you can get a dense image, and it means that it's not happening. More questions on William categories? No questions? So let's take 15 minutes break and then do limits in a category. We'll just leave the recording here, so we don't need to remember to use it.
להבין קטגוריה?
לא.
מה התנאי של להבין קטגוריה?
שתמיד יש לך קרן פרוטון.
שקיים, אוקיי.
לכאורה אמור להיות ממוצע.
לא, אז אתה ביקשת לתת לי.
יש גלגולים מודלו.
פניתי למישהו בפייבר, והוא אמר שיש הקלטות.
אוקיי. טוב, צריך לדבר עם פיינברג, או כבר לא פיינברג, הוא אומר בית מסקול טיינס. עכשיו זה כאילו קוראים עובד, אתה כנראה תהיה לו. אני מבין, אני כנראה בעצם סוג שמופיע אצלי באתר, מה שאני קלנדר של ההוראה, ושם יש קלנדר של ההוראה, קלנדר של ההוראה, עכשיו יש. אני אף פעם לא נפגש במודל, אני לא אחרי השיווק.
אם יש מישהו ש...
כן, אני חושב שבביקורת, כן, ההקלטות, תגיע יותר את ההקלטות, קצת יותר תענקות, קצת לדעת מה להפיור.
פסיה זה קצת יותר, אני נכנס קצת יותר לדיאגרמות, ודווקא הפנה אותי רק אני בדיוק זה עם פאנקטורים, משהו ברמה. לא, כאילו, האם יש פשוט שימוש של כל הזמן? הוא קצת ספציפי, יודע מה דיאגרמה. עם ההגדרה של זה כן אומר, מה דיאגרמה? זה זרקו את זה בטיפול, הקטע של ה-Universal Properties ו-Universal Objects, זה בדיוק כל דוגמא של אותמה, אבל הוא סתם קטגוריה, בוא נביא מהניש על אובג'קט. כן, למה זה, זה כל הטק, ככה 50 פעמים, האם יש לי שימוש של כל הזמן? וזהו, מה זה כאילו היה בסדר, אז אני יכול לחבור.
אני יותר טוב, הוא פשוט יתלה את האנשים.
כן, תמיד יהיה בצד. הגרון? כן. ועם הדיאגרמה, אז תראה, זה הכל.
זה היה פתאום.
אז כל הקיר הזה ספוגר. אבל כל הדיאגרמה. גם פעמים כאילו לעשות לעצמי, נגיד אם יש לך פרוסט שלך, נגיד נג'ורל נאמברס, כאלה דנאט, ואז יש לך קונאט, ואז יש לך קוקונאט, זהו, עושים את זה. איך כמה אני פחדת שוקולד, בעצם. גם הגדולה של אימא שלי יותר משלפו זה נכון לכל אפס, פעם ספציפית, אני שאומר שזה נכון האימייל שעובר התקרנו של הקופיה זה נכון רק בעדתי קטגוריה
זה אחת ההגדרות המקובלות של אימייג' לאנטיפקטורס. אלה של קטגוריות, מצד שני לכל קטגוריה יש גם מושג של אימייג'. אני די משוכנע, או פריש די משוכנע שהם קטגוריות לקטגוריות, אני אבדוק את זה, תשאירו את פוטו.
למטה של קטגוריות עם אפס גם אפשר לתת
אפס פשוט לא יהיו קטגוריים, ואז כדי ללכת עליי בהגעה של אימייג' ולסמי אל תלך. כמה שתי דקות? 3 דקות. Okay, recording it on. So now I wanted to talk about limits. So we talk about initial object, and cop object, push out. And so they're all special case of something more general called co-limit, and product, terminal object, etc. Special case of. So let's start. What we want to start with co-limit probably. So suppose we have a diagram. Interesting. And do some stupid diagram, but you can do it for any diagram. So I want to define the notion of co-limit. So co-limit, the idea is that it's something that at the end of this diagram, that everything in this diagram maps to this something. So everything in this diagram maps to this. So in the community diagram like this. Not community, we have a diagram like this. Now, I don't want it to require it to be commutative because the initial diagram is not commutative, but I want to require it to that any errors that I add in a commutative way. So what do I actually want to require? That all these little diagrams. How do you not commutative diagram? I forgot. So all these little triangles that we added, now how many of them? Okay, here is another of the I can draw it so the outside triangle, or the new triangle that we added, out with it. So let's define it no in a more coherent way. So let's call it the under category of the diagram. So it's like under category, it's like we add under category of an object. So over category for the object. Under category, it's a diagram maps to the object. So let's define it. So under of a diagram D. So what are the options? So what are the objects? Objects is a collection of. So what is diagram D? Diagram D. So it's two maps. So we have the shape of the diagram, the shape gamma have vertices and edges. So we have a map from variable from this to C. So these are the objects we here. And map of E from C. That's that. That was each edge should correspond to a map between the corresponding objects. So this is the D. And now let's define gamma tilde. V tilde. So what is V tilde? V tilde is V union with additional object. Yes. And E tilde. So you can guess what it is. It's E union with here with V the edge. We add all these edges for the V and the additional option. So this gives us a new shape. So object here will be diagrams D of the shape gamma tilde. Okay. Diagram of given shape in a given category is below this. Such that when we restrict D to gamma. Let's go it now. No, F. We'll stick F down. We go D. Here we fit with writing quality because we just bring something very basic. And you just get the same diagonal for. And for any two alpha, beta in the vertices of gamma, F what? Nothing else. Here. No. I don't know. What's fine? Over there. So F the diagram of shape gamma tilde, it means that for any vertex of gamma tilde we get an object, and for any edge of gamma tilde we get both of them. So F of the edge alpha P, we have this edge, it's an edge of gamma tilde. And then I have F of the edge alpha beta. And we want to propose them in what direction? First we perform beta. So for any edge E, I get it down alpha, any edge E that connect for any E that connect alpha and beta, there might be several that connect alpha and beta. So we do F of E and then we do A like this. This would be equal to F of alpha. Then yes, alpha P is beta P is an edge and alpha P is an edge, so we want these conditions. This so these are the object of the new category of Now we want to define. So is it clear how we write the category?
Let's do it in the brackets. F of alpha.
F of what?
No,
Here
but
alpha P.
alpha B.
So the edge alpha P. So here we have all these edges, alpha P. And for all alpha, all vertices alpha, the each time we have in the original diagram, yes, this is gamma, each time in the original diagram we have edge between alpha and beta, then we write this equal. So what it means that all the little triangles that we added are committed. So we run over all, we take the category of all diagrams and extend the original diagram with some other object and maps to this object. And such that all triangles that we add then are committed. The original diagram, if it's not committed at the beginning, it's not committed. And now we can take the limit of the sorry, now we defined objects. Now we want to define morphisms. So and for this we need to define morphisms between non-commutative diagrams. Oh no, just I will say what are morphisms here. So morph between F1 and F2 of the morph all phi in morph F1 and 2P. So all the morphisms between the two additional objects that we just had, such that all the triangles will be commutative. So let's just try to draw it where F1 of P, F2 of P. So these are the two new objects in the diagram. Now we have D of alpha and D alpha. for any local term gamma. Now here we have f1 of alpha p. Here we have f2 of alpha p. Meaning that morphism that correspond to the edge between alpha and p. And here we have phi. This commitment. And maybe here I also should divide it like this. Now, alpha of d of alpha, d of beta, f of p, e of e, e of e, not e, f. Of beta. This diagonal is instead of writing this way, put it here, this line. So we define the under category of a diagram. Now we define the limit of the diagram, the direct limit of the diagram, the co-limit of the direct over the diagram D, of over the diagram. Often you will write here the here you can write the shape of the diagram, so you run over the shape of the diagram, but take the limit of the object itself. This is by definition the initial object under the so initial object L such that L with all these morphisms, such as all the little triangles are commutative, and such as for any L prime, so its initial meaning that for any L prime with such maps, there exists a unique map between L and L prime, which make all the new triangles. Let's do examples. How do we describe the initial object as a limit of some diagram? No guesses?
The diagram is just a map from one object to another. And if you extend,
Diagram is just a single object.
If you have single object, then the limit going to be this object. Because you want to map from this object to another object, and any other map requires to this, so basically. So the answer is the simplest possible answer, but it's too simple so for you to guess it. The empty gap. No objects, no else, just nothing. So we have initial object in the category of L with no else to L, so just L. Okay, couple. What's the diagonal in couple?
X, Y,
This is
yeah, just so
diagonal of this shape. Two objects X, Y, no maps to them. Just the couple. The initial object in these things will give you couple. And push out. The limit of this diagram is a push out. And okay, these are all the examples that we did. Now, of course, once we have limit, you have also once you not limit, co-limit of this diagram, direct limit or co-limit. I already apologized last time. The need for offered terminology. Direct limit is co-limit, and inverse limit is limit. So limit is the co-limit in the object. So which basically means that L is here before everything, and it maps to everything else. So it's like limits are going backward. But for some reason we call it this co-limit. And older terminology we call this inverse limit because it actually went backwards. And but if because product is a special case of a limit, so this is why we call it limit, we call it special case of limit. So this is what.
Wait, so we define limit or column?
This is co-limit. Direct limit, which is also co-limit. And okay. So, example of limits are terminal object, product, and file.
Like the limit means terminator in the category of
Terminal object in the over category of the diagram, meaning things that are labeled to. And so what do we okay, so what are the more the new examples of limit is like at the beginning when people consider limiting categories, and the main example for why it's actually called limit is limit of diagram which looks like sequences. So you have like infinite sequences of this type, and then you can consider co-limit of this diagram, direct limit, or inverse limit, but then you want it to go back or the arrow to be organized. So what are good examples here? So here probably the best examples are of limits. So who knows what are periodic numbers? You don't know? Okay. So here is the definition of periodic numbers. You take Z modulo P. Now you can map to it Z modulo P square. Z modulo P means multiply P equal to 0. So of course, if P square is equal to 0, then you can work that way. So you can take modulo MP and then modulo P cubed, etc. And you take inverse limit of this here. What do you get? It's really hard to explain by words. What do you get? You get element which is defined by modulo P. Then a choice of a way to lift it to modulo P square. So you could have just ignore. Maybe I should say what is the inverse limit in the category of sets. So I defined what the limits in general, but what is inverse limit? Or what is directly? Maybe we should start with directly. So we have suppose that all those guys are sets. How to define L? You get directly.
Section.
In a sense, but of what? They're not all subsets. It's subset. So direct limit, you first start with union. Sorry, it's not direct limit. You first start with union. You want element here, element here, element here. Oh, sorry. You want all to be mapped to L. So L is something that resembles a couple. Yes. So we start with this joint union of all objects here. But this will not satisfy the commutativity of this diagram because we have net from X to L and we have net from W to L, but they will not be the same. The equivalence relation. Then it's like equivalence relation. Two maps are considered to be the same if one is matched to that, then they're the same. So L is a union of all these guys, modulus is equivalence relation. So in general diagram, if you just don't know anything about the maps, then this relation might not be equivalent. So, okay, so you make up. Like we did with common. Yes, so maybe I should have started with example of calling of limit, inverse limit, which limit, and we call it simpler in case of sets. So what is the limit of a diagram? No, because co-limit was disjoint union model some equivalence relation. So here we should do the opposite. So the opposite thing, we can start with a portion. Element here, common element here, like a choice of element in each guy. But not any choice will be okay because we know want now this little diameter. So we just want to require that this element go to here, this element goes to here, to this element, this element here, this element here, this element here. So limit of the diagram is the choice of elements in each object for sets, such that each element goes to the corresponding element in the other objects once you put the arrow. I could forget another two important examples, equalizer and equalizer, which are also good.
Is a limited analysis limit.
Okay, so if you want to think about limit analysis, you want to think about such example of sequence, and I think it's possible to, it's probably possible to make a category of points such that limit analysis will give it. I don't know how, but it does give you this intuitive idea that it's something that in the end, so it does make sense to call it limit analysis because it's something that what happens far away.
And one diagrams is the quick localizer is the problem of
Those with this diagram, the limit going to be equalizer and the column going to be a constant.
I need an arrow to go from the equalizer to y. The definition of the
So equalizer is an object here and the map here, and these two compositions are the same. And so you can think about an object with a map and another map like this, which has to be equal to each of the compositions, so in particular the same. And co-equalizer is what you put in. It's a and of course I forgot kernel and co-kernel. Kernel is also a limit. Kernel is limit of what? You have x, you have y, you have 0. So limit. Oh, in fact, kernel is also a fiber product. So it's limit of this diagram, which is 5. And co-kernel, that's the opposite. And you have x. Kernel. So kernel is co-limit. So kernel is limit. Co-kernel is co-limit. Kernel is limit of limit. The co-kernel is in fact push out of this diagram. No, I think something wrong. It's not can be push out of the diagram. It should be push out diagram. So push out diagram. Yeah, like this. Yes. Yeah, with glue, we can take the union of y and 0 and glue everything that goes here to y to everything that goes here to 0. So glue everything. The English is 0. So push out of this diagram with the co-kernel and the limit of the prior product of this diagram is it. So is a kernel. So kernel is the limit of this diagram and co-kernel is the limit of this. Okay.
co-kernel is the code limit of the above diagram, which is also the
Co-kernel is the column of the below.
below diagram, which is also the
Push out of the diagram. Push out is like two objects over under the first top. Right. So this defines your co-kernel, this is the kernel. Now, so now what is limit on a set theoretical level? So let's go back to such diagram of this shape, not necessarily this. So you need to choose element in each of these guys, such that each element goes to the corresponding element in the previous one. And one thing you can see once you have a diagram of this shape, then it's kind of stupid. You don't really need to choose the element here defined by the element here. And you don't need to choose the element here defined by the element here. But you don't have one object in the end. So you need to start somewhere. So you could start with 0, but each final sequence doesn't give you any new information. You can just erase any piece in the beginning of your diagram, and you will still have exactly the same. So you have this diagram, and what is so now not only the shape, so it's a choice of element modulo p, choice of its lift to p square, a choice of its lift to p cube, etc. So any integer number give you all these choices. But and if you're only interested in like finite piece, then of course every sequence of choice can be done by an integer number. But in general, it's not true. So for example, you can write how you write integer numbers, you can write them in base p. So usually we do it in base 10, but you can do it in base p. By the way, this works also for not prime numbers, so you can take p equal to 10, but just you will not. Okay, you can talk about 10 adic numbers, but it's less for. So, but let's now take p equal to 10. So when you choose a number modulo p, modulo 10, it means that you know what is its first digit. Now you have to lift it to a number which is well defined modulo 100. So you need to know what is the next digit, etc. You can write here many digits. But if you just talk about integer numbers, so at some point you have to stop. But here you don't have to stop. You just take an infinite sequence of digits going to the left. It's not like decimal. If you want to write it in a decimal way, it's like there are infinitely many zeros here. But to the left, you can do whatever you want. These are exactly the 10 adic numbers. So usually people don't discard 10 adic numbers because you have 10 adic numbers which are not 0 and they're positive 0, which is bad. But if you work with a different base, say 7, then you get the 7 adic numbers, the integer 7 adic numbers. So it's not all the 7 adic numbers, but this a big piece of them, which is known usually by this leak. Yeah, so I think sometimes you denote by ZP like this group, but it's not a good idea because this is not from notation. So
it's the limit of all these fields.
it's not fields, only this field, the rings. So it's a limit in the category of unital rings, but it's also a limit in the category of sets and limit in the category of Boolean groups. So you can choose whatever category work. Usually with limits, it's okay to change the category and you will get the same answer. With colimits, it's usually a bad idea to change the category. And you get different answer, but of course, it's just the way we think about these objects. Any example that we have, we can have the opposite example, which. So this is then one example of the limit. Another example is a poor-finite completion of a group. Who knows what is poor-finite completion of a group? Okay, so let's get it. We'll have you have a group G, and then you consider the following diagrams. It will be now a very big diagram. You have vertex is going to be arrows like this from group H at the one to the left portion, and we want that H to be finite. Yeah, and H is going to be what we expect it to be map slash diagram. So new diagram with factor category, your diagram now with factor category that we don't for another factor category. vertices of finding groups together with quantum maps to them, maybe not only find probabilities on probabilities, yeah. And the edges are maps if we find groups such as diagrams of groups. And then you take the limit of all this. So if you would range over all groups in the world, then you will get one of the groups will be just G, and the other will be identity. And this will be an object in your graph, or it will be initial object of this category, so it means a vertex in the graph which have error to all the other graphs. And once you have such a thing, you have a unique error to all the other guys, and once you have such a thing, this is going to be the limit of the category. And this is something that nicely know if you have some limit of the diagram, if you have some very complicated diagram with many things, but then you have here an object with just map to anything in the diagram, then you can forget about the diagram because when you do the limit, you do the over category of the diagram, so you have some object element with the map here, and to the all other objects, but it's already automatic because you just can take the position and you know that this is what you will have to do because the diagram is unique. So you take a terminal object in the over category just of this first object, which is just this object. So once you have the initial object in the diagram, then you're done. Everything is finished. And in this case, you have U1 over all. In this case, if G is finite, then you have this G, and then you do. But if G is infinite, then G itself is a quotient of G, but not finite. So you take limit over all finite things, and you get something that's called the post-finite completion of G. It's something that G maps to it, but G is in fact the limit of a larger diagram where you allow all the groups. So it maps, just because it maps to each of the HI, so by definition it maps to the limit of H. But itself it's not G. G has its own G. And the best example probably is Z. So what is the profile completion in G? You need to range over all onto map from G to another group. So how do we from Z to another group? How do we define onto map from Z to another group? What's what?
It should be over tablets. And make a product from them.
You're absolutely right, but this is for you. And this is just the end of the question. Now, at the beginning, I just want to ask you what I asked. Just ask us what are the onto maps from Z to final group?
For that to that model to end.
Yeah, if we are going to map from Z to a final group, it means that this is a quotient of Z by some normal subgroup of Z, normal subgroup of Z, a subgroup of Z n times Z, or 0. But the quotient by 0 is not finite. The quotient by n times Z is finite. So this is our object in the diagram. So we take the vertices similar to here, will be Zn for all n's. But the errors will not be that simple anymore. We'll have error from n to k only if n is divided by k. Yes, when we have a map from Zn to Zk, when n is divided by k. So we will have this diagram as one of the pieces, but we will have this diagram for any p, like one of the pieces, and in fact we will have much more objects like products of 2 primes, 3 primes, etc. But one can see that like the most important part is this diagram and the next diagram for 2, for 3, for 5, etc. And then when we take limit of all these diagrams, so here each time we get that 2, that 3, that's 4. So we can take like image of each diagram separately, get ZP, and then take limit of this discrete diagram with all that p's without errors between them, and then we get Z. Z hat, which is the product or Z. Yes. So this is Z hat.
How is this called again?
Z hat, usually Z hat
You
is
said something completion. What is the word?
profile conclusion. So groups which are if this map is isomorphism between group and its profile completion, then the group G is called profile. And profile completion of a group is always profile. So Z itself is not profile, but its profile completion is. Okay, so these are the limits. Maybe I should tell about notion of cofinal and no, not cofinal. Yes, coffee. Okay, I don't remember the name, but you already noticed that sometimes part of the diagram can be erased and nothing will happen. So you already noticed here, for example, that you can take the subset of erase the first 10 elements and nothing happens. And you notice that in the diagram of this shape, you can erase everything which is not the initial object and nothing happens. So a subset of objects in the diagram is called, I think, cofinal if no, I don't remember the name, so there are of course two dual notions. So if any vertex in the diagram have an arrow from one of the objects in the subset. And it's and you have a dual notion when you have an arrow. And then, okay, now one has to be a little bit careful not to erase too much arrows, but basically you can replace the diagram with this subset of objects, adding the correct amount of arrows, and the limit will not change. And limit or colimit depending on what size you're going to. And this is very convenient, for example, and this is a way you can define when you do Z hat, you can basically go into limit only over these objects, and I don't know, it will be enough, but from it's more complicated. Okay, but you have many examples when you can erase, like you can erase the beginning and you don't change anything. So questions about limits? No questions about limits. Do we have examples of limits? Probably not. Okay. So we can start the next chapter because we have another 10 minutes about functors. So what is a functor between two categories? Actually, we have D. Or the functor between C and D. Basically, what you would expect to be. It's a map between OC and OD. Then L for N and Y of C. You everything more X to Y X. So as usual, we use notation. We use the same letter F to denote the functor itself, to denote the corresponding net between two objects, and the corresponding net between two between most between two objects. So sometimes we put some index, sometimes we just write F of C will be just the region. So this is called functor. This is like morphism in the theory of categories. And indeed, you can consider the collection of all categories. And it's indeed category, except of the is with a theory, but let's take collection of all small categories. this is not a small category, but it's a category. Because you can compose functors, it's clear what combination means, you have the identity functor, and all the axioms are. But this is not a good notion, and because, for example, in this category for categories, you will have the notion of isomorphism. Notion of isomorphism will be functor to one direction, functor to the other direction, so that the compositions are equal to identity. And the equality between two functors, you already see that it's a bad idea because it's like talking about equality of two objects. You can define it, you have the notion of isomorphic categories, but usually not going to be something that we want to discuss. For example, let's talk about quality of functors. You have the functor of direct sum, or product, but just one. The functor of product of sets, x times y, and then x times y, that set. So this set and this set are not going to be equal, and it's kind of bad because we do consider the third-digit product as something associated.
Does F preserve composition values?
What?
Does F
Yes, of course. Yeah, I forgot to say. Yeah. So functor is a map like this, a map like this, which maps the identity element to the identity morphism to identity morphism, and composition to composition. So in particular, if you have a category with one object, which is a monoid, then functor between two such categories will be homomorphism of them.
the inverse mappings?
In general, category doesn't have to have inverse map, so you don't require to do it. But since you map identity to identity, if you do have inverse maps in both sides, then functor maps them. So now I want to. So I said that okay, functor between two categories C and D. So first of all, on the technical level, it's often not a set because it's too loud, but let's take C and D. Small categories, then this is a set, but it's a bad set. It's a set where you have many different elements which you want to consider them to be equal, but they're not. And so what it is actually, it is a category. So we have category of functors between two. So what is morphism of two functors? The morphism between f and g. This is the following data. It's phi here, so it's phi x. So for any x in C, or any object in C, you want to have phi x such that the following diagram or diagrams will be commutative. So if you have here x, so if you have here y, so here you have f of alpha and here you have g of alpha, where alpha is a normal from x to y. So you want this diagram to be commutative. So again, morphism between two functors is a collection, a pair of a morphism between the value of one functor and the value of the other functor, such that all such diagrams. So in all the books, and we're going to see today that people from algebraic topology call this natural transformation. So natural transformation of functors, but it's not that there is a reasonable notion of other transformations. But these are the morphism of functors, but just when it was first defined, so the people that defined it didn't want to talk about the category of functors. It was weird for them. So I think at that point they didn't define category at all, and just defined the notion of functors between existing categories, like how it was topological spaces in books, and then they say what are natural transformation between functors between topological spaces and groups. And of course, very fastly they understood the category here, but we still stuck with this notion of natural transformation as if there are some other. And another bad thing about this notion that in math you also or often like to say about some object that it is nature. So we didn't depend on any choice, that it's something that you didn't invent it, that had to be there. And of course, morphism between functors sometimes arise this very natural way, but sometimes there are many other morphisms which are not canonical, not natural in any other sense. So I think this name is a bit misleading, but and I see today usually people not really use it, we just say morphism between the functors, but still some people do this. Questions?
What are the definition of like what conditions need to satisfy the functor between the function between the mole xy and mole fx?
This function?
Yeah.
Yes, so it's something European I didn't say. So we of course want that f x y of say phi composed with f y z of c is equal to f xz of c convolution phi. I hope I did I did the direction for and of course x of identity x equal to identity f of x. Maps identity morphism, so identity morphism and maps composition. Okay, so more about functors next time.